Hello, I'm Ed Hughes, the Product Manager for SAS Optimization. The solveBlackbox action was introduced in SAS Optimization 8.5. Let's explore the ways in which adding this CAS action enhances the capabilities of SAS Optimization. Here's what we'll cover. We'll start with a brief review of Blackbox Optimization and how it surfaces in SAS Optimization and elsewhere. Then we'll compare the new solveBlackbox action and the Blackbox Optimization solver. In the course of this comparison, we'll look at a few examples. Finally, some concluding remarks. So what is Blackbox Optimization? Well, in some ways, it's easier to say what Blackbox Optimization isn't. It isn't traditional optimization, which always depends on some simplifying assumptions. For example, all linear programming algorithms, or LP algorithms, assume that the objective is linear, all constraints are linear, and all decision variables are continuous. They can take on any value between their lower bounds or their upper bounds. Other traditional optimization algorithms, for example, in mixed integer linear programming or nonlinear programming, also depend on assumptions about the functions that appear in the model and the values permitted for the decision variables. Blackbox optimization is different. It makes no assumptions at all about the decision variables or the functions in a model it's solving. The only requirements it places is that any function in the model can be evaluated at any point the solution algorithm encounters. That's all. Other than that, it's wide open. Functions don't have to be smooth. They don't have to be continuous, differentiable. And that last point explains why Blackbox optimization is sometimes called derivative-free optimization. In really extreme cases, the function you're dealing with might not even be a function in the usual sense. There might not be a closed form expression for it. You might evaluate it by looking up the value in a table, and that's fine as well. The positive side of Blackbox optimization is that you can use it to address an essentially unlimited range of problems with two caveats. First, remember that this is a heuristic solution method, meaning that it isn't guaranteed to find an optimal solution. It almost always finds a very good solution, though, and that's often more than good enough for practical use. Second, owing to the nature of the algorithms in this class, you should limit its use to problems with no more than about 100 decision variables. The negative side is simple but significant. When the assumptions of traditional optimization go away, the limits on what problems you can solve largely disappear as well. But you also lose the benefits of those assumptions. If there are no assumptions about what kind of functions you're dealing with, you can't tailor a solution algorithm to work well with that kind of function. So no assumptions is simultaneously the best thing and the worst thing about Blackbox optimization. This isn't a reason to stay away from the Blackbox approach. It's just something to be aware of. In fact, there are several cases where you clearly should consider using Blackbox optimization. If your problem doesn't fit into any of the traditional optimization categories, and you can't use traditional solvers. So for example, a mixed integer nonlinear programming problem. We'll look at one of these later. Or if you're working with multiple objective functions simultaneously. For these problems, the BlackBoxSilver finds a set of non-dominated solutions, in the sense that for each solution in that group, there's no other solution that has a better value for every one of the objectives you're considering. Or when you can use a traditional optimization solver, but it's not producing a good solution. The general rule here is to use the solver that's the most tailored to the problem at hand. If you have a linear program, it's best to use a linear programming solver. Choose Blackbox optimization if your problem doesn't fit with a more specific solver, or if a traditional optimization solver isn't working well. So Blackbox optimization augments your toolbox of solvers, but doesn't replace traditional solvers. The Blackbox optimization solver was formerly known as the local search optimization, or LSO solver, and that's been a part of SAS optimization for a few years now. The original name came from the fact that local search, along with global search, is an important component of the solution approach. We renamed the solver in SAS Optimization 8.5 to reflect the fact that it can deal with functions that are essentially black boxes. It doesn't matter how the functions are evaluated. You just have to be able to evaluate the functions at any point you encounter. Genetic algorithms, which maintain a group of solutions and use genetic operators to evolve the population of solutions over multiple generations, provide the basic framework of black box optimization. The global and local search elements operate within this framework, and they enhance it as well. Looking beyond SAS optimization, black box optimization is also used by SAS visual data mining and machine learning to tune its hyperparameters. The solveBlackbox action supports the actions in the auto-tune action set. Now let's consider how the solveBlackbox action compares to the BlackBoxSilver. With the BlackBoxSilver, you use op-model syntax to set up the entire model: index sets, parameters, decision variables, constraints, and objective. This is true whether you happen to be using proc-op model in CASL or the run-op model action in CASL or any of the other languages, Python, R, Java, or Lua. With the solveBlackbox action, you have more options and less elaborate modeling support. You move away from op-model syntax, and you can use the action's parameters to declare decision variables and linear constraints. Any nonlinear functions in constraints or in the objective, well, those you define using a block of CASL code that you designate with the eval subparameter. So there's a little bit more of programming burden here, but in return, you get a large amount of flexibility that op-model just simply cannot offer. We'll see more about that in a moment. Indexing is a big advantage of op-model syntax because it lets you refer to members of vectors and arrays in a really direct, readable, clear way. There's no indexing in the solveBlackbox action, but you can use the indexing capabilities of the language you're using. The paper includes a Python example. If you're comfortable with op-model, then keep using it and the BlackBoxSilver. If you're more proficient in one of the other languages, then the solveBlackbox action is probably a better choice for you. And in fact, here's that Python example I was talking about. So let's look at a quick example of indexing. If you need to declare 8 binary decision variables, y1 through y8, and you're programming in Python, this is how you could do it. That's a lot of code. Code involves the solveBlackbox action, and it declares the entire model, including those 8 decision variables. As you can see, the bulk of the code is devoted to just declaring those 8 decision variables. But if you're already comfortable working in Python, and this is probably why you'd be using the action in the first place in Python, then you could use a simple loop to declare the set of decision variables before invoking solveBlackbox, like this. And you'd have a much more compact and more easily maintainable code. In fact, the Python code that declares the decision variables is just about as compact and direct as the corresponding op-model code. And if you're wondering, in Python, range 1.9 halts when I equals 9, so it creates 8 decision variables in all. Now let's talk about another advantage of the solveBlackbox action, multilevel parallelism. And this is part of the flexibility that the eval equals code block provides. In this case, let's say you've defined a nonlinear objective function. The nParallel parameter enables you to define how many objective function evaluations using that eval equals code block can run simultaneously. The n subsessions workers parameter lets you specify how many worker nodes each one of these evaluations can use by itself. This means that multiple parallel function evaluations can each execute multiple CAS actions in parallel. You can't achieve this kind of parallelism with just the run-op model action. Even better, let's take a step back and consider this on a more basic level. You're evaluating a nonlinear function as part of solving an optimization model. You can call a CAS action to accomplish this, again in that eval equals code block. In fact, you can call CAS actions on multiple levels because of this multi-level parallelism. In op-model, at least as of SAS Optimization 8.5, you can't call even one CAS action to evaluate a nonlinear function. So in return for a little more programming work, you gain a huge amount of added flexibility. Now let's look at an example. Let's say you're a researcher who's created a Gaussian process regression to fit three-dimensional input data. That's 3 independent variables and 1 dependent variable. To do this, you use the GP-reg action in the non-parametric Bayes action set in SAS Visual Data Mining and Machine Learning. But before putting the model into production use, it's probably a good idea to stress test it. You know the upper and lower bounds of the independent variables, and for this test case, you know the data comes from a three-dimensional sine function, which lets you compute the actual value of the dependent variable at any point. You can get the estimated value from the regression model. So the question is, how large could the model error possibly be within these bounds? Well, you can use optimization to find that out. The objective function here, the model error, is the absolute value of the difference between the estimated value and the actual value. To compute the estimated value, you need to call the score action. You'll also need to call 3 other CAS actions. And as we've seen, the solveBlackbox action enables you to do all of this. This is the program that first builds the regression model and then stress tests it using the solveBlackbox action. We're going to run the whole program, but for now, let's skip past building the regression model and go straight to the stress test with optimization. That starts right here. But don't worry, the entire program is included in the appendix of the SAS Global Forum paper. What you see here is the CASL code block that computes the model error for any point as defined by the values of the independent variables x1, x2, and x3. Y is a dependent variable. In line 95, the error is calculated. Now notice the calls of the various CAS actions. The save result action in line 83 creates a results table that holds those x1, x2, and x3 values. The score action in line 87 calculates the estimated y value. The fetch action in line 90 moves the estimated y value to the results table. And the drop table action is used in line 99, cleaning up in preparation for the next call of this code. Here's the solveBlackbox action call that sets up and runs the optimization model that maximizes the regression model error. In lines 112 and 113, you can see the value of the objective function error is calculated by calling the code block we just looked at. Notice n parallel equals 20 in line 116 and n subsession workers equals 2 in line 113. This means that up to 20 objective function evaluations can run in parallel, and that each one of those subsessions, one for each evaluation, can use 2 worker nodes. That means up to 40 worker nodes can be used in parallel. Now, how much parallel work is actually done, how many nodes are actually used in parallel, is going to depend on how many nodes happen to be available in your session. Let's run this program. And we'll scroll down to where the optimization results are. And what we see here is the maximum error, which is the optimal objective function value here. We're trying to maximize error, is a little more than 0.75. Keep in mind, though, that the regression model is estimating a sine function, which only ranges between -1 and +1. As a result, the maximum error of 0.75 is really a cause for concern. And that probably indicates we should revisit the regression model. Because Blackbox optimization is a heuristic solution method, it isn't guaranteed to find an optimal solution. However, it will virtually always find a very good solution. In some cases, though, there can be a distinct difference in the quality of the solution that Blackbox optimization returns, depending on how it happens to be used. We'll see that the solveBlackbox action gives you more options in this respect. One example is this mixed integer nonlinear program, which has a mix of binary and continuous decision variables, a nonlinear objective, and a mix of nonlinear and linear constraints. For this problem, we happen to know an optimal solution. and its objective function value, the optimal objective function value, is minus 0.94347. In our first solution attempt, we're going to try to solve the entire problem using the BlackBoxSilver. We use proc-cas and the runout model action. Here's the block of op model code that the runout model action executes. You'll see that it declares the binary y variables, the continuous x variables, and it also declares the nonlinear objective function and all the constraints, linear and nonlinear. Finally, it calls the BlackBoxSilver. Let's run this section of the program and see how this all-at-once approach performs. Scroll down to the bottom of the output results, and what we see is that this approach identifies an optimal objective function value of about minus 0.668. Well, this is disappointing because we know that's nowhere close to the true optimal objective function value. Let's try something else, a new approach. As we've already seen, if you use the solveBlackbox action instead of the BlackBoxSilver, you have more options available to you. Remember that with the solveBlackbox action, you can use a code block, a CASL code block, to evaluate an objective function. And this CASL code could include, for example, just running one of the traditional optimization solvers in SAS Optimization. Well, that's exactly what we're going to do here. Here's the strategy. The solveBlackbox action is going to assign values to the binary y decision variables. And then it's going to call the NLP solver to solve for the continuous x decision variables and evaluate the objective function. Remember, you need values for all of your decision variables in order to find out what the value of your objective function is at that point. The reason this works is because once you assign values, zeros or ones, to the binary decision variables, they drop out of the model. And it is no longer a mixed integer nonlinear program, it's a pure nonlinear program. And that's something the NLP solver is well suited to handle. This is the CASL code block that receives the y variable values from the Blackbox optimization and then uses the NLP solver via the runout model action to solve for the x variables and find the objective function value. Here at the bottom of the program is the call of the solveBlackbox action that solves for the y variables and then calls the code block we just saw. It passes the y variable values along as input. Let's see how well this approach does. And good news. This time, we find a solution that has the true optimal objective function value. Now, really, in practice, you won't be able to predict with certainty whether the solveBlackbox action, using that to segment the solution method, like we've done here, is going to do better than using the BlackBoxSilver to tackle the entire problem. But the solveBlackbox action provides you with the flexibility to attempt this kind of an approach. If you use the BlackBoxSilver and for some reason you're unsure, unsatisfied with the solution it produces, go ahead and consider a modified solution approach as appropriate, like we've done here using the solveBlackbox action. You might find a better solution, or you might confirm the solution you've already found is optimal. Either outcome is going to be worth the investment of time and effort. As we've seen, the solveBlackbox action is a valuable addition to SAS Optimization. It broadens the scope of programming languages you can use to express optimization models, and it also significantly widens the range of problems you can solve. It helps you make much more effective use of parallel computational resources in solving those especially challenging optimization problems. And lastly, in some cases, the solveBlackbox action can help you pursue innovative solution methods that can find even better solutions. I hope this presentation has been helpful. Thank you very much for your time.